Hello, everyone, and welcome. So today we'll continue with conservation of energy, and we will solve the rest of the suggested problems. But I want to start with like a quick reminder of this week's material. So Monday we started with defining conservative and non-conservative forces, and we introduced potential energy as an addition to previously defined kinetic energy. And we showed that this energy, kinetic energy, plus the potential energy, which we called the mechanical energy, was conserved if there was no non-conservative force in the system. So some problems, and later we introduced conservation of total energy, including the mechanical energy and other energies like dissipation and internal energies. And we show that energy is conserved even in the presence of dissipation if you take the dissipation into account properly. And we introduce gravitational potential energy in a more general form with the inverse score law. And we introduce some other definitions like power, and I showed you that you can look at the potential curves and then describe the motion. Okay? There are some questions. Does the conservation of energy hold in non-inertial frame of references? Yes. Conservation of energy holds in all frames. It's one of the strongest laws in physics, so it holds no matter what. Here is the problem. Show that the total mechanical energy of a satellite of mass m orbiting at a distance r from the center of Earth, let's call the mass of Earth me, is given by this. If u is equal to 0 at r is equal to infinity. And B, show that although friction causes the value of E to decrease slowly, kinetic energy must actually increase if the orbit remains circle. What is this 1/2? Interesting. So, okay, maybe I can draw Earth. First, let's do this. Maybe it's the blue planet, so it's the blue. Okay, this is Earth. Now we are thinking of some orbital like this. Okay. And this is your satellite. I don't know, let's say it's orbiting like this. Okay. Some V, and satellite has a mass m, and Earth has a mass m Earth. Okay. Maybe I can center this a little bit, but that's fine. Now, so what do? I know, okay, and these two guys, maybe I can pull this guy a little bit. So this is the center, this is Earth. Earth. And these two guys are at a distance r. Okay. So first, find the kinetic energy in terms of Gmm. Okay, let me find the kinetic energy from Gmm. But how can I do this? If r goes to infinity, then potential becomes 0. Yes. Then potential energy at a given r, I will write it like u of r is equal to, what did we say? Minus G m Earth over r, right? Is that correct? Yes. Now, kinetic energy is, okay, kinetic energy, maybe I don't need to ask you, it is 1/2 mv squared. And we are interested in total energy, which is E is equal to kinetic energy plus potential energy, which is equal to 1/2 mv squared minus g m earth divided by r. Good. So what are we happy? So what is the next thing to do about this? Exactly, right? So now we don't know V, so we want to express V in terms of this guy. And for this, exactly like you said, we use centripetal force. Centripetal force is in the circular motion, mv squared over r, and this guy should be equal to the force. But in the case of gravitational attraction, we can take the derivative of this potential and find the force to be g m earth divided by r squared. Let's do some cancellations. M r, then v squared is equal to g me divided by r. Now I can plug this guy in here, right? I can put an expression for v. Sorry, there's no m. So this guy, there's no m. Okay. We cancel the m's. If I put this there, E total is equal to 1/2 mv squared. I just write exactly what I see here, me over r minus g me over r, and this is equal to what? This is equal to minus, surprising, minus 1/2 g m over r. Okay, where did 1/2? So let me follow if I missed anything. So this is 1/2 mv squared, but this one is mv squared over r. This is like centripetal force, right? And this should be equal to gravitational force. And here, 1/2 coming from 1/2, m coming from m, and v squared here is coming from this v squared. So there is 1/2, and there is no 1/2 here. So 1/2 minus 1 is minus 1/2. So I want to ask you why. So where did I use this? If u is equal to 0 at r is equal to infinity, how did I use this? So it seems like I didn't use it, right? Where is it in my solution? I use this guy. So why would the question bother to say something? Why would he waste some ink for this expression? Any ideas? To find u of r, right? Exactly. So I wrote here u of r, but we said potential was defined up to a constant. It actually should be like something like constant, right? We only know the differences in potential. That's how we define the potential. But once you give me this information, once you give me u is equal to 0 at r equal to infinity, I can put this constant to 0, because I can put r equal to infinity, this guy goes to 0, then this constant must be 0. That's how I found it. Okay? So this is A. So let's talk about B. Show that although the friction, there was so far no friction, but let's switch on some friction and show that although the friction causes causes the value of E to decrease slowly, kinetic energy must actually increase if the orbit remains a circle. Interesting. So B is kind of like friction. Okay. How can we understand friction increase kinetic energy? That's weird, right? That's strange. Generally, friction slows things down. Now it seems like not really. When E decreases, R must decrease too, as other variables are constant. So since K is proportional, that's exactly what it is, right? Thank you. That's very accurate. So we now think about friction, right? Somehow there is like friction. And friction should actually decrease total energy. That's what we know, right? If there is friction, there's some sort of dissipation, then the total energy increase, right? The decrease. So we know total E should decrease, right? Now, how can I decrease the total energy? Decreasing total energy means E is equal to 1/2 mv squared minus g m e over r. This total thing should decrease. But from the previous problem, I know this part is actually dependent on 1/r2, right? It is actually proportional to, this is like, since mv squared over r is equal to g m over r squared, v also depends on r. Okay. Now here's how we do this. We are saying that if there is dissipation, and if this guy goes to a little bit inside in the orbit, right? Like this, just a little bit. Like this. My total energy is here. Where is my total energy? Here. Here's my total, minus 1/2 g m e over r. So if r decreases a little bit, or if what am I saying? If r increases a little bit, sorry, there's like a minus. If r decreases a little bit, total energy will increase, right? Increases for decreasing r. But if r decreases, that's the catch, the force, centripetal force increases, right? If you go to like a smaller orbit, you get a bigger force. But if you get a bigger force, that means you have to get like a bigger circular velocity. So this is first step. Second step, if r decrease, F, I don't know, central will increase, and if F central increase, V increase. So if you decrease R, this whole thing, yes, increases, but since there's like a minus, energy will decrease. Okay? Isn't R decreasing because of friction? Yes, exactly. The friction that we are talking about here only changes R, not V. No, friction changes the total energy. So there is no law like saying that friction should slow things down. Friction should decrease the total energy, right? That's how we consider friction. But decreasing total energy based on what we found is only possible if we decrease the radius. But if we decrease the radius, we see that it increases the velocity, okay? Oh, yes, thank you. This is decrease for decreasing R, yes. And if R decrease, F increase. And if F increase, V increase. Yes, thank you. I miswrote. I didn't write what I wanted to write. My hand was out of my control. So yes, let me write this table. I think it's easier to write it than say it. So R decrease, going down. E, based on this equation, total E, if R decrease, E decrease, right? E decrease. But if R decrease, F force mv squared, G over R squared increase. Because if these two things come closer together, the attraction gets stronger. But if F increase, V increase. This is actually a lot of words to say, but I mean, saying it is actually harder than solving it. So if you sit down and solve it, you'll see it's not that complex. So here's the problem. So draw a potential energy diagram U versus X and analyze the motion of a mass M resting on a frictionless horizontal table and connected to a horizontal spring with stiffness constant K. The mass is pulled a distance to the right so that the spring is stretched a distance x naught initially, and then the mass is released from rest. Okay, I think this is a lot of words again, but we can, so there's like this, there's some spring, there's some mass, and this one is stretched some x naught. It will stretch. How do I spell stretch? I guess something like that. SRT. Okay. Initial position. Okay. So we need to draw U versus X. X, okay. U is equal to 1/2 K X squared, yes. So U is equal to 1/2 K X squared. Something like this. Maybe I can use a different color. Okay. And this one is plus x naught. This one is minus x naught. Draw a potential energy diagram U versus analyze the motion of mass M resting on frictionless horizontal table and connected to horizontal stiffness constant K. The mass is okay. And so initially the mass is here. And okay, of course, this is like U. And initially mass is here. As soon as you release it, it's going to start going to center. And as it goes to center, its potential energy will decrease, whereas kinetic energy will increase, right? Maybe I can do something like that. So kinetic energy will be reverse of this. Maybe I can use a different color for that too. I think some people like it that way. Okay. So let's use red for kinetic energy. And green is U of X. Red is K of X. Okay. And so your particle goes like back and forth like this. I can do this. So this is the mass, goes back and forth like this. So as it goes from here towards the origin, the kinetic energy increases because the particle speeds up, and the potential energy decreases because one half here, the x decreases. And here, this is the minimum potential. There is no stretch in the spring, but there's like a speed, so it's like a maximum kinetic energy. So it doesn't stop, so it starts compressing the spring. As the spring is compressed, it's going to slow the particle down, but it's the kinetic energy will be converted to the potential energy, so you will increase, the kinetic energy will decrease. Okay, that's what it is. So the spring of this problem has a stiffness constant like K, and mass is 5 kilograms, is released from rest when the spring is stretched 1 meter. Determine the total energy of the system. A, okay. So this one, I think the suggested problem is 76, but 76 was referring to 75, so I had to write both of them. So A, okay, this guy, A, total energy of the system, E, total, I think we now know that if we can just put 1/2 k x max squared, right? And this one is going to be equal to, I think we'll just plug in numbers. Let me do this. 0.5 times k 160 times, and x is nicely in meter, so it's like 1.0. It's equal to 80 Newton meter or joules. Maybe I can add joules. Okay. B, okay. B kinetic energy when x is equal to 1/2 x naught. Okay. B when x is equal to 1/2 x naught. U, I think I can calculate ux is equal to 1/2 k square of this 1/4 x naught squared. Then kinetic energy is equal to, maybe this is like E total minus U of x, which is equal to 1/2 k xm squared minus 1/2 k 1/4 x naught squared, and this is equal to what? 3/4 1/2 k x m squared. But I know what 1/2 k m squared is, so I'll just multiply this number with 3/4, so to 60 joules. That's B. C, maximum kinetic energy. So maximum kinetic energy, okay, that's K max. I know what this is, 80 joules. And D, maximum speed, and at what point, I think we already said where it occurs, but speed is like 1/2 mv squared is this K, V max, K max. Then V max is equal to 2 K max divided by m square root. So I can do this. Okay, clear this, 2 times 80 times, okay, actually not times, but divided by m. M is equal to what? 5 is equal to this, and I need to take square root, 5.6 meter per second. So as ABC, D maximum speed, okay, this is ABC, D, and occurs at x is equal to 0, and E maximum acceleration and where it occurs. Okay. E, how do I find this acceleration and where it occurs? So maximum force from, exactly, good job, thank you. Yes, thank you all for that. So max acceleration is obtained for maximum force, then A max is equal to F max divided by M. This is equal to K times X max divided by M, and that's equal to, I think we can find that. I found 32 meter per second square. And if we are, okay, maximum acceleration, they are not saying where, but I think it occurs here, right? At this point, because that's the point that it just here occurs at x is equal to minus x naught. Or if the sign is not important, it occurs 2 points here and here. So Chris jumps off a bridge with a bungee cord, a heavy stretchable cord tied around his ankle as in figure. He falls for 15 meters before the cord begins to stretch. His mass is 75 kilogram, and we assume the cord obeys Hooke's law with K given. If we need that air resistance, estimate how far below the bridge Chris's foot will be before coming to a stop. Ignore the mass of the cord. Okay, not realistic, however, and treat Chris as a particle. Okay, we are ignoring his size. He's just all of his mass is accumulated in his foot, and we want to find. Okay, let's see if I can get this done. Any ideas? How do I do this? So he is like, and I want to find delta y. Okay. If you need to estimate how far below the bridge. I think it's kind of asking what h is, right? What is h? Okay, mgh, maybe I can write it. So mgh, like we are taking our reference point to be like this. Okay, reference. So I'm writing energy according to that line. Mgh should be equal to. So when he's here, it is completely spring energy. So it's like 1/2 K, and it's like delta y squared. Is that correct? So from this, delta y is equal to 2mgh divided by k, right? And we need to take the square root of this. But the problem is h is equal to delta y plus, I don't know what to call this. Let's call this length of the cord, L, right? So then delta I is equal to 2mg over k times delta y plus L. Then does anybody know how to get y out of this? So I have y here and delta y here, but I want to find delta y. So, and delta y is given in terms of delta y. How do I pull this delta y out? Square of both terms, right? And yeah, okay, good. So delta y squared is equal to 2mg over k delta y plus L. So delta y squared minus 2mg over k delta y and minus 2mg over k times L. I was thinking if it was a way, there was a way to get rid of this quadratic form. And how do I solve this quadratic equation? So delta y is equal to, does anybody know? How do we solve quadratic equations? Yes. Minus b is 2mg over k plus or minus squared b squared 4m squared g squared over k squared minus 4 times 1 times c, which is minus 2mg L over k, and this whole thing divided by 2, and this is 2mg over k plus or minus, I think we can cancel this one with this one, this one, and this one. And write this, okay. This is m squared g squared over k squared plus 2m g L over k, right? Oh, that's all. That is over a, yes. So that's it, right? It's a little bit messy, but well, that's what we get. And now the question is if it is plus or minus. So maybe I can take this inside the parentheses mg over k. This one will be 1 plus or minus square root. So 1 plus, okay, mgk 2L over mg over k. I write k here. Okay. And is it plus or minus? Which one? Why? Why not? Right? So when I write it in this form, it's clear, right? When I take the inside the parentheses, and see put it in this form, you can kind of tell what it is, right? It's not like it doesn't take too long. So I'll put plus. Yes, exactly. If you put minus, the output becomes minus, and we kind of started with this one. Oops. We want this one to be positive, like because we are measuring the distances. Okay. So it's asking for h. So if this is the case, then h. Okay, let's choose a color. H is equal to delta y minus L. Okay. Should I put these numbers in? Maybe you guys can put the numbers in and tell me what it is. Maybe I can do this. Okay. You found 55 too? Good. it should be 55. Okay. If you found 55, I believe you are 55 because my calculator arrangement is really messed up. So this is 55 meters. Then this one should be 55 minus 15, 40 meters. Is that correct? Thank you. So thanks everyone for coming. That's it for today. If you have questions or comments, I'll be around. If not, I'll see you next week.